Okay, well, thank you for coming, and I'm happy to see a little bit more attendees than usually. As this, you do hear well with this setup?
Yes.
Okay, thank you. So we are continuing to acquire the density functional theory fundamentals, and we are about halfway through. So after acquiring the theorems and some background information, we are going to jump into algorithm and then to observables. So at the end of this chapter, we will observe that the practical implementation of density functional theory is very similar to what was designed for Hartree-Fock, but it gives some benefits compared to Hartree-Fock in both precision and the amount of numerical resources spent much more economic. So for administrative part of the course, I'm always planning to upload some handouts, but sometimes I'm late with them. Let me know if you really need them. It is just supplemental information to what we are discussing in lectures. There is a little verbal homework distributed to a week ago, and it is due today. No one else submitted it. I was checking it an hour ago. But that's okay. It's really short. Everyone will be able to complete it. And I have composed another little verbal homework which will be based on comprehension of today's meeting. Today we will meet. You all are invited to go downstairs to Arts and Science basement, room 16B, and we will cover additional topics for treating the output of WASP software, and today we will focus on spin, also treat unrestricted situation when amount of electrons with spin up and spin down are different. Maybe we will cover this classification of singlets, doublets, triplets, and how it can be treated in WASP software. And also, we may cover the subject of partial charge densities, which are analogous to molecular orbitals. Number of then when we meet in the basement of Art and Science a week later, next Tuesday, we will cover the subject of molecular dynamics and dispersion. Then on coming Thursday, a week from now, you will share your experience doing those things. Should be okay, not too challenging. Okay, so as we will see today and maybe next coming Thursday, the density functional theory originally appeals to density only, and there are theorems that everything can be expressed in terms of density. Actually, there are so-called orbital-free density functional theory, which is actually the only pure DFT theory. So it does exist, but vast majority of scientists do not use it because it has substantial disadvantages. So of course, this orbital-free DFT, when energy is actually expressed as functional of density, it works really well. It scales much better than any orbital-based method, but it has some difficulties in predicting chemical bonding at all. So it is very efficient for big chunks of metals. But if we want to describe molecules, it is maybe it needs another 40 years to be developed. And the advantage, the big step forward, it was suggested by Kohn and Sham, is to use the benefits that are promised to us by theorems. Not all of them, part of the benefits from the density function, from the ideal density functional theory. But do not neglect the positive experience that we already got from orbital-based theories, from Hartree-Fock and all those semi-empirical. So actual Kohn-Sham DFT is not, cannot be rigorously classified as pure DFT. It is some sort of a merge of this previously developed orbital-based computational chemistry methods and a lot of benefits from theorems from pure density-based density functional theory. Here I just recall that last time on 2 previous lectures we overviewed the theorems that density determines everything and that ground state density provides minimal energy, right? But the difficulty with those theorems that this dependence of energy as functional of density is not known. It has been proved that it does exist, but it is not known. And the theorems do not promise, they do not give any software that will efficiently predict properties of molecules and materials. So there is a very big distance between proving the theorems and implementing them for real materials. And the actual advantage of this people, Kohn and Sham, is to develop an algorithm, develop a procedure that connects these ideals and gives a way to predict properties of materials. They developed an algorithm that later different scientists implemented for practical computations. Okay, so we'll try to focus on several key steps that are important on the way from the theorems to practical implementation, to the algorithm. So we will need to get a little bit more acquainted with concept of functional derivative, which is if we understand what functional is, then functional derivative shouldn't be a problem. Then another very important thing is a trick that Kohn and Sham committed. So they made an artificial switch from system of many interacting electrons to artificial system of non-interacting electrons. And it is hard to believe. They gave some argument, and finally one does see that it works in practice. But it is something French or common sense. And there is another little cornerstone for their algorithm. Actually two. So they reintroduce back the molecular orbitals, and they are using them for 2 purposes. As an auxiliary tool to compute kinetic part of the energy, and as an auxiliary tool to build, to construct actual charge density. And the practical ways how these two steps are done also need to be covered, need to be discussed. Reintroduce molecular orbitals auxiliary roles. Kinetic energy and the way to construct density. Construct density. Okay, so we need 1, 2, 3, 4 items, and then after we get them, we can line up an algorithm. Actually, what is the core of all pieces of software that do DFT calculations? Those 4 points are not yet do not serve as an algorithm. They are practical, little practical steps to be able to build the algorithm. Just if you're impatient and curious, the algorithm is in simplified form is here. One gets a self-consistent loop of going from density to potential to orbitals and then back to density, computing energy total in between. But we will get to it later. Oh, okay. I think I have already pronounced all the stuff. It is just verbalization here, so that one needs to use orbitals for kinetic energy. And this is just a consequence of this assumption, so that if orbitals are used for kinetic energy, then anything else in the total energy will be treated as a functional. Okay, so concept of functional derivative. There is a calculus. There are operations of integration and differentiation. They are conjugate to each other. If you take function, integrate it, and then differentiate back, you obtain the same function with precision up to a constant. And similar operation can be formulated in terms of functional. When we were describing the way how interaction between electrons and ions contribute to the total energy, we agreed, or we derived, that one can combine all ions, number I minus ion number I, summation over ions. So making a term like this, which corresponds to attraction of electrons to nuclei, and then convolute it with the charge density. So from physical background, we set up the way for term in the functional that is responsible for attraction electrons to nuclei. Let's look on this operation in a little bit more mathematical way. So we are having density and here increment of volume, increment of position. We can probably introduce this increment under introduce the density under sign of differentiation, so that we have derivative increment of total density. And here we see the functional, the potential, and increment increment of density, right? Let's remove the integration sign. Then on the left part, we'll see an infinitesimal increment to the energy term due to this operation. And on the right side, we'll have the infinitesimal increment of the density. And now we can make ratio of them and say that it is a limit when this change of density delta rho goes to 0. So ratio of increments for total energy in respect to increment of density can be referred to as functional derivative by analogy to usual typical differentiation. And what we get out of this operation is typically serves as a potential in respect to science, in respect to physics, in respect to chemistry, electrons, and ions. And I think that there is a chapter in formal math that functional calculus, where if one takes this course or spends years in research, one goes much more further in these things. We need just first step. Okay, so these two operations are conjugate to each other. So one can generate potential out of functional and back functional out of potential. And what is appetizing, what is convenient, what is useful for our future steps towards Kohn-Sham procedure, that this operator that we are getting can enter some eigenstate equation. And eigenstate equations, it is something that we were well versed since many years. We were trying, one tries it in any discipline that is related to quantum properties. So an opportunity to use this potential back in the eigenstate equation is a little technical benefit. We also have a way, we have a formal procedure to get this potential out of the functional. So if we are in the world of density functional and we are trying to describe something, we are not speaking about operators and Hamiltonians. We are speaking in language of functional of energy and different terms in the functional for total energy. But the meaning of those terms, the physical processes are the same as in our previous life. So we have a term for kinetic energy. We have a term for one electron nuclei to electron attraction. And we have a term for electron repulsion, right? The three terms that we got after Born-Oppenheimer separation for electronic part. So this term is most straightforward. We just discussed it again. The kinetic energy is promised to be treated by some special way, but just in case we could use something in the spirit of Thomas Fermi theory. Just use it as density to the power whatever 5/3. And here is a permanently challenging term of electron-electron interaction. So it can be split onto three parts. Two parts that we are aware due to our experience in Hartree-Fock theory, and one new term that does exist, that in some systems it is important, but we were neglecting it up to now. So there are Coulombic terms that correspond to repulsion of a new electron contributed to the system from the background charge distribution. Right? There is an exchange term that corresponds to antisymmetry of multi-electron wave function, and incorrect account for this exchange is a major step forward in Hartree-Fock theory. And there is an additional term that we are neglecting up to now. This term is really small. In most chemically important systems, it is negligible. It becomes important in magnetic systems when different magnetic centers interact with each other. Then it becomes one of the leading terms. But in vast majority of practical applications, it is not so important. So in case electrons interact in a weak form, or in case the charge density of each electron in the system already has an imprint of the background interaction with remaining background charge distribution, one can think that bringing new and new electron will view the product of total density just as a product of independent density. Same as in a simplest approximation as wave function can be viewed as a product of orbitals. And for densities, it is a good approximation. And it is good as long as one can believe that multi-electron density is a product of single electron density. But as soon as this assumption violates, one needs some additional correction term. And the formal measure to account for this deviation is to take some actual experiment or a method that of much higher rank that everyone believes, and compute total energy with the absolute precise methodology. Then compute the total energy based on this product factorization. And the difference between those two will be referred to as correlation energy. And, I'm going to reproduce a phrase that I do not understand, but I've heard from a respected person. So this correlation means that two electron distributions cannot, even distributions cannot occupy same spatial locations. And if there is a extended system, then they perform motion subsequently going to one place. If one electron goes into another place, then another electron is going away from there. And they feel their presence and try to avoid each other in a more precise way. But this sounds strange to me, just reproducing. The formulation here is correct, and it is accepted as standard.
Oh, Dr. Killian, how is the correlation term different than the Coulomb term? Because you're talking about both of them having repulsion.
Correlation is more dynamic.
Okay.
Coulomb is already taken into account in a single electron picture.
Okay.
So when you bring a new electron in system that has already several electrons, the shape of charge distribution that is taken by new electron does have an imprint of rest of the charges that were contributed before.
Okay.
And if one needs some more detailed additional precision, then one is looking for those correlation effects.
Okay, thank you.
Let me maybe make a little example. So if you have two functions, and each of them, let's say that they will be the same. Sine square y. Then we build a product of those. Or if you're speaking about densities, let's know them. Y. And then we do the cosine goes this way here, and this way here. Then isocontours will have a maximum in the center, and then they will become smaller and smaller as we approach the borders of the box. But in reality, we have a shape square f square y times exponential x minus I y squared. Then isocontour of such function will be not so symmetric. It will consolidate along the main diagonal. But in many situations, this effect is very tiny and not important. Just to be general, one needs to take it into account. Okay, so with all this level of complication, one is realizing that it would be so much more convenient to have independent and non-interacting electrons, so that this benefit is inducing any intellectual effort that can bring us to this situation. And let me show the trick that Kohn-Sham did in order to achieve this situation when electrons are efficiently non-interacting. So this is not reality. This is a trick. So the theorems claim that for given density, one has a given total energy. So this is accepted. But the way how they are connected leaves us some degree of freedom. We can vary the way how we connect density and energy. And even the way how we repartition the terms in the total energy functional can be tweaked. And what this gentleman suggested, they told that, okay, let's assume that our electron-electron interaction term is multiplied by a parameter that is smaller than 1 and bigger than 0. And the one electron term does depend on this parameter. So the real world that we are observing on experiment corresponds to situation when lambda is equal 1. So we have the electron-electron term in place. But here is the trick. The idea of this trick is that they suggested to repartition weights the relative contributions of one electron term and many electron term. And they suggested that let's repartition the weight of these contributions in such way that the total density stays the same and total energy stays the same. So we repartition the contribution of terms, but keep the sum the same. And then there are two limiting terms, two limiting cases. One limiting case is a realistic universe when we have full-scale multi-electron interaction, and another ultimate case when this lambda parameter is equal to 0, meaning that electrons do not interact with each other. But one is doing this procedure in such a way that density and energy are the same. One designs a parallel universe where electrons do not interact with each other, but in this parallel universe one gets the same total energy and one operates with the same total charge density. It is not dictated by the laws of nature. It is a human design, human contribution to make the calculations easier. So in real nature, one cannot avoid electron-electron interaction. It is a setup that makes such a pseudo-auxiliary universe that will give same results as in the real world, but in much simpler arrangement. One keeps same density and same energy. Okay. So for lambda equals 0, one does have only kinetic energy and the term in the functional corresponding to single electron. Electrons do not interact with each other, but the total functional should be the same. And this sounds crazy to me, but it is what they did. And this one electron term has to keep an imprint of everything that was before, of all multi-electron interaction, meaning that if we take the difference between total energy and kinetic contribution, then everything that was contributing before total energy should be re-partitioned, should be refunneled to this term, which needs to depend only on single electron properties. One subtracts kinetic energy from total energy and tells that, okay, it is a effective, fictitious, auxiliary, one electron functional. And now we apply our new friend, the functional derivative, to vary this one electron functional in respect to change in density and get a potential. So it is a potential that rigorously one electron construction, but it could be designed, again here, by now we do not provide practical ways, but it could be designed in such way that it will reflect the multi-electron nature of the system. Okay. So if we returning back from the language of functionals to language of operators, then it is very tempting to express something, to write down something in terms of eigenstate problem. If we do have this potential, we have we can consider it as an operator, and we do have an operator for kinetic energy, then we can formulate, not telling that we will use it for practical computation, just telling that one can use this kinetic plus rest of energy operator as a tool to find multi-electron wave function. Not our real multi-electron wave function, but something in the parallel world where individual electrons contributing to this function do not interact with each other. And this is analog of time-independent Schrödinger equation, but it is not Schrödinger equation because this potential is not real. It is fictitious from parallel universe. So we do have a way to determine wave function. And here there is a second step which doesn't have anything tricky. It is a logical continuation of original trick. In case the electrons in this parallel universe do not interact to each other, then this fictitious Hamiltonian can be split onto individual terms. And one can set up a way to independent variable approximation, to separation of variables. And we go from here to separation of variables. So, although we agreed that this potential is the same for each electron, our kinetic energy formally is defined as multi-electron operator. And this fictitious Hamiltonian does depend on many electrons, many arguments. But what was done by Kohn-Sham is to split this multi-electron Hamiltonian onto smaller, less important partial Hamiltonians for each variable. And then these little Hamiltonians are looking like kinetic energy plus this potential, and they can be used as a tool to set up some lower order eigenvalue problems to find some one-electron orbitals, which again, this all is not real. This is auxiliary tools. So they can be used to find one-electron orbitals. But since potential is recorded, otherwise it is independent one electron Hamiltonians, and each of them can generate one electron orbitals. But since the electrons do not interact, since the potential is the same, solutions for those lower order eigenvalue problems will be the same. Orbitals obtained for each electron, set of orbitals obtained for each electron, will be the same, will have the same form. And now we do have the following players in the game. So we have the fictitious multi-electron operator that we obtained as a functional derivative from the total energy. And it is able, it can generate multi-electron wave function. On the other side, we do have one electron partial operators. They can create a set of one electron orbital. Since it is something not real and it is not determined for a specific molecule, it is auxiliary construction by Kohn-Sham. So they should keep responsibility for their design. Therefore, those orbitals are referred to as Kohn-Sham orbitals. And this wave function and those partial one electron orbitals are connected in a usual way. So the instead of solving this multi-electron equation, one can solve only one electron equation and then build the multi-electron wave function as Slater determinant of that accommodates products of all occupied one electron orbitals. One electron orbital. Okay. Do you feel that we are approaching the glorious completion of the task? Or not yet? We are missing an important part. So we are still wishing to use benefits of density functional theory. Benefits in computational sense. We want to hire someone who can establish a practical connection between density and total energy and incorporate this connection into the calculation schematic. So we are not forgetting about benefits of density function. We just made a little step aside towards wave functions, but we are going to return back. And in order to use those benefits, we need to construct total density based on those Kohn-Sham orbitals. So when we will complete this step, we will be ready to set up an algorithm, and probably the actual algorithm will be presented on our next meeting. But today we are going to complete this little task. There's a little verbalization of what we already have. The orbitals are fictitious. Formally, those orbitals are not interacting. So by now, we do have definition of functional derivative. We have a new potential that reflects total energy minus kinetic. We have a Kohn-Sham Hamiltonian and Kohn-Sham orbital. And now we are going to determine total density based on these orbitals. Okay, any ideas? What is one electron density in case we do have multi-electron wave function? How can we build density out of wave function? Any suggestions? How do we build probability density if we have one electron wave function? Don't hesitate. Aren't we taking some power of it? Huh? Yes, absolute value squared. So if you have an orbital, one electron orbital, then we take absolute value squared and we call it as one electron density, right? The density functional theory makes an equal sign between probability density and charge density. And this step is also not justified by all research community, but it is very helpful in predicting properties of material. So, density equal question mark charge density. So if you are very cautious, do not speak it out loud in the community, but it is one of the assumptions that is used in density functional theory. But what if we have a multi-electron wave function? If we agree with this step, how do we build multi-electron density?
Sum of atomic orbitals?
Huh?
Sum of atomic orbitals for...
But more general, if you do not know atomic orbitals, if you just have a multi-electron wave function that depends on many electrons, many independent coordinates.
Integrated?
Yes, we need to take absolute value square first, right? So if you take absolute value squared, then it will be multi-electron density. And if you want to separate, to make it depending only on one variable, only on one electron, then we need to integrate over the rest of variable, right? No objections? Okay. So if we need multi-electron density, we just take absolute value squared or wave function conjugate. And if we need one electron density, we, for example, depending on R1, then we take this construction and integrate over all but one. Integrate over R2, R3, and all independent variables, right? Is it easy? Does it look easy for practical implementation? Probably not. We want to do anything possible to avoid playing with actual multi-electron object. So there is a way to show that this complicated thing can be substantially simplified. Why do we need it? We need to use total density, electron density, for using functionals, for using benefits of functionals in density functional theory. And we have paved a way to set up very useful building blocks, Kohn-Sham orbitals. So now we want to build total density out of those Kohn-Sham orbitals that construct many electron wave function. And the question is, if this total density expressed in terms of multi-electron wave function, which is expressed in terms of Kohn-Sham orbitals, will look in some simple, easy way. Can we simplify it? Well, we are trying to avoid actual multi-electron functions, but let's do an example of minimal multi-electron wave function consisting of two. So we do have function 1, function 2, variable 1, variable 2, and because electronic wave functions must hold antisymmetric property, we are building a Slater determinant. So not just a product, but this determinant which will include permutations. Then we are going to plug this thing into definition of density, and density will be plugged into here, and then we will just look how the one electron density constructed through all this sequence based on Slater determinant will look like. So this is our target, and this is our starting point. Begin, here, end. Ready? Okay, start, set, go. So we do have one, two, R1, and you can try to do it independently. It could be a very good. This exercise could be a very good candidate for some homework or whatever midterm. So taking diagonal minus subdiagonal. So this is a wave function of R2. Now we need a conjugate, which means that we just add the star on the top. This is there is much more writing than actual thinking. It is more calligraphic exercise. So you see that in the second term, the arguments are swapped. So we need, at this point, we need to multiply this one, this one by this one. It is so much easier to do it when with a copy-paste option, some editor. So we have product of two factors, and each factor consists of two terms. So there will be total how many terms after we open the bracket? Yes. And we are going to integrate this thing over, let's say, dr2, so that the result will be depending. So the result will depend only on R1. What do we expect from this construction? We will open the bracket, we will observe 4 terms, and then we will perform the integration over the R2 variable. And there, the component, the factors that do depend on R2 can be either coinciding, providing delta function equal 1, or different, providing delta function equals 0. So integration over R2 variable will help to cancel some terms. So instead of 4 terms, we will get much more compact expression, and we will get less terms, less factors and less terms. Okay. So here's we didn't make any mistake by now. And okay, let me just go shortcut. I did a homework and prepared the each step. So we have first term from first bracket times first term from second bracket, and second from the first from the second, and so forth. And now let's just look on it and see what we can integrate. So this term depends on R2, and this term depends on R2. And this one is wave function orbital number 2, and this one orbital number 2. So integration over R2 of these two things will be delta T2 will be equal 1, right? Let's look on the second term. We have this one depends on R2 and this on R2. Here it is orbital number 1 and orbital number 2. And when integrating them together, you'll get delta 1, 2 equals 0, right? So here we have orbital number 2 depending on R2, and orbital number 1 depending on R2. If we integrating them together, we are getting delta 2, 1, which is also equal 0. Then here we have this and this term, first orbital, and when we integrate them together, we'll get delta 1, 1 equals 1. So we are getting rid of second and third term, right? We are getting rid of integration because we already completed it. And then, so here is something useful and important. After these operations, we removing two terms and several factors, and I'm going to highlight the terms that are remaining. So theta 1, R1, theta 1, R1, theta 2 of R1, theta 2 of R1. So they all do the only remaining terms depend on variable R1, what it was our original setup. And we do not have any crazy cross terms. We have just product of one electron orbital conjugated to one electron orbital. So it is very helpful, very useful result. We didn't prove it for more than 2, but it is very expected that the construction will be the same. So instead of something really crazy, multi-electron determinant like, we get a simply summation of probability density of charge density for electron in each occupied orbital. This is really beneficial. So rho of R1 is orbital 1 squared, orbital 2 squared, if you have a system of 12. And generally we can say that if it is more than 2 electrons, we just summation theta sub I absolute value squared gives us total density. So as soon as we develop maybe computationally, as we compute those auxiliary one-electron Kohn-Sham orbitals from the parallel universe, we can immediately build our real true world charge density. And out of this real charge density, we can build a real total energy. So we are returning from all these abstractions to actual world that helps us to predict properties of material. Auxiliary tools, real world total density and total energy. And I suggest that we are going to stop here, but for our next meeting, we'll see that those two things, I should point there on the screen, those two things are helping us to find the potential and to find the orbitals. And orbitals, in their turn, allow us to find those two things. And we can go in a loopwise way. Orbitals help to find density, density help to find energy, energy, potential, and then orbitals back. And through cycling, we can do a refining and get better and better energy at each step. And this is a major advantage of Kohn-Sham procedure, Kohn-Sham algorithm. We are going to focus on it in more details when we meet on Thursday. So I suggest we stop here, and I would be happy to answer any questions. If there are no questions, then meeting is dismissed.